Now we come to a proposition where we can actually link the notion of Artinian and Noetherian very tightly. So let A be a ring in which some finite product of maximal ideals, which are not necessarily unique, is 0. Then A is Artinian if and only if it is Noetherian. So being Artinian and Noetherian coincide if there is a ring in which finite product of maximal ideals becomes 0. And this will essentially boil down to vector spaces over fields. And in vector spaces over fields, so finite dimensional vector spaces over fields, the Artinian and Noetherian condition coincides. So this is what this will boil down to. So what we do is we start with the 0 product of maximal ideals. So say you have this AP, which is just product of M1 all the way to MP, and this is 0. So this is ring A, which has some finite product of maximal ideals, not necessarily unique, but the product is 0. And then we can set AR as M1 all the way to MR for R less than P. So we have a chain like this, a descending chain. So this is our ring A. So this is A1 just generated by one maximal ideal, A2 generated by product of M1 times M2. So it is contained within M1, and then A3 is generated by M1 times M2 times N3, so all the way to AR, and then to AP, which is just 0. So these R's are all less than or less than P, or less than equal to P. We can set P in the end. So now we can consider some subspace. So we can consider AR minus 1 over AR. So you can see A1 lies over A2, and you can see AR minus 1 is just ahead of AR. So this AR minus 1 is product all the way to MR minus 1, and AR is just M1 all the way to MR minus 1, then times MR. So essentially just copying this right here. So recall that M is Noetherian or Artinian if and only if M and M modulo N are Noetherian or Artinian. So in fact you have a short exact sequence like this. So N is a submodule of M. You can modulo it like this. So this is Noetherian if and only if this is Noetherian and this is Noetherian. And same thing can be copied for Artinian, because essentially what we are saying is that the lattice of chains here and here are coming from here. Or you can say you can combine lattice of chains here and here to come here. So this is essentially just a condition on lattice of chains. They just pass along. So this we have discussed thoroughly for Noetherian case, but the same proof follows for Artinian case. So for translating into our case, we have this MR sitting right here. So this becomes AR minus 1, this becomes AR. Now, so MR is, as a module, it is a module over a field which is A modulo MR. So notice that only MR sits here. So it is a module over a field. And so we can talk about its chain of submodules. So what is its chain of submodules? So its chains of submodules are in one-to-one correspondence with the ideals contained within AR minus 1 and AR. So between these two ideals, so this is contained within this. So between these two ideals, there could be a chain of ideals. So that chain of ideals corresponds precisely to submodules of MR, because they are just modulating AR minus 1 over AR. So whatever chain of ideals is there in here is precisely the chain corresponding to submodules of MR. Now if A is either Noetherian or Artinian, then MR will satisfy chain conditions. So it will either satisfy ascending chain condition or descending chain condition. Now if it satisfies ascending chain condition or descending chain condition on the submodules, this will make it into a finite dimensional vector space in either case. So essentially the idea is that MR will become a finite dimensional vector space. So this is the key, and we will prove this in a bit after you complete the proof. So we have to prove this key, and the proof is very easy. So we have to prove this key. So idea is this MR, once we know that it will satisfy a chain condition, and it has to satisfy a chain condition because uh, this AR minus 1 will also satisfy the chain condition. It is just lying in a chain, so it will satisfy the chain condition. AR would satisfy the chain condition, so this MR has to satisfy the chain condition. Just essentially we are just using this result on the top here. So MR will satisfy the chain condition. It could be Noetherian or Artinian, and the idea is that once it satisfies the chain condition, it becomes a finite dimensional vector space. And if it is a finite dimensional vector space, we have talked about this before, then it is both Artinian and Noetherian. So on a finite dimensional vector space, this you have Artinian if and only if Noetherian. So the only thing left is to just show properly that this is a finite dimensional vector space. So now we know that this MR is both Artinian and Noetherian, and then we can repeatedly use the following. So this, if M1 and M2 are Noetherian, then their direct sum would be Noetherian. If M1 and M2 are Artinian, their direct sum would be Artinian. So this we have showed in the Noetherian case, and the proof will carry over to the Artinian case. So we can carry this result to make this entire ring Artinian or Noetherian, because this ring is just made out of these modules. So ring A is just made out of M1, which is A1 modulo A2, direct sum with M2, which is A2 modulo A3, so small pieces of it, and so on all the way to in the end you just have AP left, and this is just 0. So yeah, so you're building this A piece by piece, piece by piece, piece by piece, and each of this piece is both Noetherian and Artinian. Each of these pieces is both Noetherian and Artinian, precisely because each of this piece is a finite dimensional vector space. So now we come to the important lemma which we mentioned in the proof. So let K be a field and V be a K vector space. So this V was our space MR, and our field was A modulo MR, where this MR was a maximal ideal. So MR was a vector space of where this is a field. So then the following are equivalent. 1. V is finite dimensional. 2. V satisfies the ascending chain condition, and 3. V satisfies the descending chain condition. So that is this ascending chain condition, this Noetherian condition, and the Artinian condition, they become equivalent for a finite dimensional vector space. So 1 immediately implies 2 and it implies 3, because you can use composition series for our finite dimensional vector space, and which will immediately satisfy ascending chain and descending chain condition because it is a finite composition series. Now for the opposite case, we have to show that 2 implies 1 and 3 implies 1. So the easiest way to show is that is by contrapositive. So not 1 would imply not 2, and not 1 would also imply not 3. So this is same as this by contrapositive, and this is same as this by contrapositive. This is the not sign. So not 1 means that V is infinite dimensional. So if it is infinite dimensional, then we can choose a sequence of linearly independent elements. So these linearly independent elements are xn, n greater or equal to 1. So let un be the space spanned by x1 to xn. So then we have a strictly ascending chain. u1 is contained within u2, so this is just x1, which is contained in x1, x2, and so on. So this is an infinite chain. So this is strictly ascending chain. So that means V would not satisfy an ascending chain condition. So you get not 2. So now for not 3, you consider the space Vn. This is a subspace spanned by xn plus 1, xn plus 2, and so on. So we have a strictly descending chain. So V1 is, you have x1, x2, x3, and so on. This will contain V2, which starts from x2, x3, and so on. this will contain v3 which will start with x3, x4 and so on. So there is the containment like this, but it will keep going on because you have infinite dimensional vector space. So we have a strictly descending chain. So there is descending chain condition is not satisfied, so it does not stabilize. So does not stabilize. So this is not 3. Again, this does not stabilize, so not 2. And therefore we have the equivalence of these 3 conditions which we just used in the proof.